this is an introduction to two technologies that I think fit perfectly together, which are zk and autonomous world. And this video is divided in two parts. So in the first part, we'll go through what is an autonomous world and how zk information asymmetry can help boost an autonomous world. And we'll also go through examples of already existing or work in progress like examples, and also we'll go through the architecture and tooling that we can use today to build a autonomous world with privacy. In the second part, is going to be more hands-on coding. We're going to do 3 examples to get you started on everything you need to start building your own autonomous world with privacy. Okay, so let's get started with what an autonomous world is. And I think the best example to get everyone started is, of course, Dark Forest. So Dark Forest is the first well-known and in this relatively new niche autonomous world, which got everyone's attention. That basically you can collect planets, and then with the energy from those planets you can collect more planets and basically build your galactic empire. And I think the interesting thing for me was how quickly alliances were formed. Like they will have DFDAO versus OrthinGG, and very recently WASM, and there are many more that started grouping together to basically make everything else easier for everyone, part of the DAO. But of course you have your opponents that you can fight or make alliances with. So I think this is very, very interesting. So not only that, but also a lot of tooling was made, different indexers or clients, depending on the alliances needs. So I think this was super interesting. Of course, it's not the only example. You have OpCraft, Skystrife, Primordium, Dope Wars, and of course the game that got me into autonomous world, which is Discourse Machine. I think this is a very new experience. Different types of experiences and gameplays are being developed right now, and yeah, there are other titles that I think are super interesting being worked on. And so, okay, so what do you need to create an autonomous world? You need composability, which means the word is able to be compatible with other words. You need also immutability, so to have the certainty that is the word, it's the way it is going to be changed in the future, and also programmability to allow the users and the players to experiment with the word and be creative. Of course, this creates a permissionless, credible, and modable word. You can think Ethereum is the tool perfect for this. And yeah, I think this is the perfect tool for this. And Ethereum itself, I think it can be considered an autonomous world. But what else can you build with an autonomous world? Okay, in the what we're already seeing, of course, is games. But in the future, very futuristic future, I think that this is the perfect place for your consciousness to be uploaded. Of course, you don't want your consciousness to be uploaded on a Amazon Web Service or a Google Web, Google Cloud servers or Azure or whatever, because this is controlled with a few minority of people. You want something decentralized, secure, composable to upload your consciousness. Of course, from games to consciousness, there's a lot of things in between. And yeah, I think at this point in time, we're very early to know what is the potential for this. This is very new, and I think this is going to continue to grow. So yeah, I think a lot of things are possible here. So let's get now into zk information asymmetry, and how everything pieces together. So I think this example is the best one for me, zk Hunt. So, Dark Forest was the first example, but there is one problem. Dark Forest, I feel like Dark Forest is more of a proof of work game than a zk game. So the zk part is because you have this word that is private, but you can hash it to like discover the word. And the parts that are not hashed are like invisible to you, but once you hash it, the whole word is public to you. This is the different thing with zk-hunt. In zk-hunt, yeah, this like full privacy game. And in this game, you can move around from a public state to a public state, which is moving around in the grass, or you can enter in the forest on the trees. And when you enter on the trees, no one will be able to know where you are. They just will know that you moved, but they wouldn't know where you moved. And that's the interesting part. Now, your units, they can attack in a dash. They can make this sort of dash in attack, and it will attack everything in between. But the interesting part is that you can attack from public to public. That can be like 100% done on chain, like on Solidity. And they can also attack from a public state to a private place. So you will need to, so the recipient of the attack will have to prove that, with zero knowledge, they will have to prove that they are not, that they survive the attack basically, but without revealing its position. That's the interesting part. And the most interesting part is that two units can attack each other from a private to a private state without revealing to the rest of the players if like their positions. I think this is super interesting, 100% on chain. So the idea is that at the end of this video, you're able to understand how this word was built. In order to do so, we're going to use this example that I built myself, which is inspired, of course, in zk-hunt, Dark Forest, and also on Stratego, a board game, a physical board game, where users can move around their pieces, so everyone else will know where every other pieces are, but they have different types of pieces. And as you can see, there is this question mark, so you won't know the type of the opponent's pieces. You will only know the position, and you can attack them, you can defend, yeah, you can have combats around it. And this is important because, of course, the different units are just have like a different range of the types that are determining how they are played. So the dragon is the strongest one, that is able to beat the mage, that is able to beat the ogre, and is able to beat the knight. But the knight, of course, is the weakest one, but is the only one that is able to beat the dragon. So the interesting part for me is that all this logic can be built on the circuits, on zero knowledge. So you can make all the combat logic in a private state. So the players won't reveal their types. So this is a typical architecture of a ZK DApp, ZK with autonomous word app, that you have the public state and the private state. So in the public state, we're going to use mod. That is a tool built on top of Solidity. So basically, it will be able to handle all the public state and all the public computation, all the game logic, all the movement of the pieces in this case. And in the private part, we have Circom that is going to handle all the combat. The combat is going to happen. The combat will preserve the user type, and it will only reveal the result of the battle. So all the combat is going to be done off chain in the private state. Of course, we're going to store some commitments in mod in the public state. By the way, mod, I didn't explain that mod is a framework to build autonomous words, and it's very convenient for us because it makes everything more composable. And we will learn from scratch how to create a mod game, and then we'll add ZK on top of it. So we're going through all of this on this video, and we're going to use a phaser UI. The phaser is a JavaScript front end that allows you to just make the rendering of the images, animations, and user interaction. But I just want to mention that all of this architecture is like a starting point. And this is something that we as creators, as developers, can give to the players or the users. And then they can do whatever they want with this. And what do I mean by this? So basically, they can build their own CLI tools. And why would they want to do that? Because maybe they want to have a dedicated prover, or maybe a cloud proof aggregation. They want to use client proof aggregation to make proving faster, or maybe they want to use their own custom indexer that is, I don't know, more efficient. Or what if they want it to be run by bots? Maybe a bot that is controlled with AI that maybe is verified by Ethereum. And oh no, we're getting run by your opponent. Maybe they want to build their own MEV tools, run their own nodes, so they can have an edge. Or what if they just want to have an alternative UI, maybe 3D, maybe with VR? They can choose however they want to interact with. I think this is pretty core to what an autonomous world is. And basically, an autonomous world is allowing the users to build a new world. And what do I mean by this? And basically, this is what I don't mean by this. And this is, I think it's very funny, but also very sad that the current incentives and the current tools that are available to creators and developers are basically are not aligned and not make easy to the consumer, the creator, to the consumer to be a creator itself. So, but I think that Ethereum can provide the tooling and the incentives that allow the players to be creators themselves. And I think this is very powerful, and this will allow a new type of dynamic and a new type of basically words to be formed. So precisely, what do I mean by this? Is that user can create their own. Is an autonomous world is a world where users can create their own system, their own logic, and maybe also their own UI. They can create their own, for example, they can interact with the phone, the browser, VR, whatever they want, but also they can have their own narratives. For example, in DFDAO, right? The DFDAO and OrdenGG was formed very quickly from Dark Forest. They created their own history of the game, their own narrative. And right now, games are very linear, and they're like watching a movie. And an autonomous world can allow like players to create the world itself with everything, like the narrative and everything. And yeah, also, for example, tooling, the indexer and everything, bots. And yeah, basically a game that is able to, that you can build on top of it with tools, UI, narrative, but also the game itself is flexible to allow people to create on top of it. In this video, we're going to use Circom combined with mod to create this world. And Circom is going to handle, as we mentioned before, all the private state, and mod all the public state. And Circom, also we can, instead of Circom, we can also use Noir or Socrates or Artworks. And yeah, we're just going to use Circom for this example because it's the one that has the most adoption, but it's not the only option that you have, of course. We're going to use mod, as I mentioned before, because it's very convenient to create autonomous world. And then where would you want to deploy this? Because the type of game that we're going to create is 100% on-chain. And this is important for the world to be immutable and secure and composable. So you want to prefer to launch in a chain that is very cheap, that may in the short term like sacrifice security for cheap transactions. And in this case, we're going to use Redstone, which is a plasma chain. Well, we're not going to deploy it. It's just like a recommendation on where to launch an application like this. There's also Base also, I think, announced another chain that's also Plasma, B3, I think it's called. But yeah, you can basically reduce the security guarantees to allow people to do a lot of more transactions. And yeah, this is where the application are being developed right now. Also, a quick mention to StarNet and Dojo, which is basically Dojo is the framework that you can use to build autonomous world on StarNet. I think this is very interesting. And yeah, we're not going to be building in this video, we're not going to be building on top of Dojo, but I think it's a good mention about it. Also, another thing that I find very, very interesting is about the future of the technology. So right now we are like in the zk era, I think we can call it like that, but the MPC and FHE era is also coming. And I think there's a very important role for autonomous world, and I think that basically autonomous world is like filled with creative people doing creative projects, and these new technologies like MPC, FHE need creative use cases, new use cases. So I think autonomous world is the perfect place for that. Also, on top of that, I will prefer personally to experiment and test all these technologies with games and experiences in a very low stakes environment instead of experiencing it with MPC in DeFi or in voting and governance system that has a lot of more on stake. So yeah, I think that yeah, I think MPC and FHE that it's coming. I think it's going to be great to experiment with them on autonomous worlds. Also, a couple of organizations to follow: Circom, of course, the creators of Dark Forest; Lattice, that is the builders of mod. They're like expanding the autonomous world tooling; and Seismic, that is looking into the new technologies, how to implement it with autonomous world. Of course, these are not by any means the only organization. So please leave in the comments some organization and cool creators of autonomous world that you know. And let's end with this quote from Isaac Asimov that reads, "It's change, continuing change, inevitable change, that is the dominant factor in society today. No sensible decision can be made any longer without taking into account not only the world that it is, but the world that will be." Okay, so thanks for sticking through this whole introduction. Let's get into the second part. We're going to build 3 demos using mod, first without zk, and then with fully privacy. Okay, see you then. Now in the building part session, we're going to do more on coding, like hands-on coding, and we're going to do 3 examples. The first one is going to be only autonomous world, no privacy, which is going to do a very, very simple like coin collecting game on mod, just to get us familiarized with mod, the framework. In the second one, we're going to do a PvE scenario, player versus environment scenario, with a backend proving. And in the third one, we're going to do a PvP scenario with WASM proving in the browser. So let's get started with our first demo, which is this game where you collect a player and you can move around and you can collect coins. And the coins will be like stored, how many coins will be stored on the state. So we're going to use Node version 20, but you can use whatever version that it's upper than 18 and should work fine. You can install that and also PNP and Foundry with these commands if you haven't yet. And so yeah, let's get started by just creating a new game. We're going to open a terminal here and we're going to just create a new one. So when you create a new one, you will get this template. It will ask you for which template you want to use. You're going to use Phaser, the front-end framework for games using TypeScript. And then the first important part is going to be the schema. So this is, so in mod, you don't use the state as you normally do in Solidity, and instead you use this table-like, SQL-like table system where you store all your data. So let's grab this and we'll put it in the mod config file. Remember that you can, if you want to follow with me, yeah, I'm going to leave in the description all the 3 articles that we're going to use in this demo. So I'm going to open, oops, I don't know what happened to my Visual Studio Code. Okay, here you go. Okay, so as you can see, you have in the package directory, you have the art where all the sprites, all the animation is going to be. You have the client. Oh, I'm recording right? Yeah. You have the client where all the user interaction is happening. This is the phaser part, and then you have the contracts where all the game logic is going to be. Remember, this is a 100% on-chain game, so all the logic is going to be reading in Solidity in this case. Not only that, but you also have the mod config file that has all the game state, all the game data, which has this default counter schema we're going to remove. We're going to replace it with our own schema. So in this game, you have 3 tables. The player position that has an XY coordinates, the coins position that is basically the coins that players can collect, and once they collect them, they will like add to the counter of coins to the player count, to the player coins. We also have some enums that you can define here. And yeah, this is what we're going to be using just to handle the player direction. You will see that in a moment. So we're going to handle the logic in Solidity, but before getting into that, we're going to remove some default files that have the phaser demo, and we're going to create this system, and systems in mod handle all the logic. So we're going to go to contracts, source, system, and we're going to create my game system file. Well, sorry, I don't have the color set up. You can see it here, that it has a function to generate coins. So basically this is just a demo. For this demo, just creating a coin in some specific places. Then when the player click on the map, it would spawn in that position, and then he can move around. And basically the logic of the game is that you can move up, down, left, right, and this will check the if you don't go beyond the map like limits. And finally, this is the code needed for collect coins. Basically, if you step into a coin, you will destroy it, and then here you destroy it, and then you will add to your player amount count. So we're also going to edit this post-script deploy, and what it is that you know that here is, so mod has these systems, and each system can, one contract system can interact with many states. So one game logic can like instantiate and control many words. So this is important because this means that constructor doesn't work the same way as in the normal Solidity project. So for having like a constructor like functionality, we need to put that into the post deploy script that that works the same way as in a constructor. So what we're going to do is that by default we're going to generate some coins. Okay, so next, into the game client interaction, we are going to put all this code that is going to handle many things that we're going to see in a moment. So we go now to the client, source, layers, phaser, system, and we're going to create also a new system here. My game system dot TypeScript. Okay, so what you will find here is the movement. So move in all the direction, basically on the key that you press, WSAD. Also, I added an I key just to continue spawning more coins if you need, just for testing purpose. And also it's going to handle all the sprites animations and how when they get into the map, when they appear, also for example coins and player when they spawn, and what happens when a player walks into a coin and it disappears, so it's going to be removed from the UI. So this handles all of that logic. Now we're going to go in through the animations, and here I have some animations. The player, this cycle animation of the player just existing there, and a coin that's going to be put all over the map. So we're going to put those into the art directory, into the sprites directory, and then we are going to package them. So basically, you usually, so for phaser, it's not very convenient to just read the PNG each file different. So we're just going to create an atlas, which is a big file that phaser is going to be able to access quickly. You don't need to worry about that because these commands will do it for you. You just need to put the sprites in the correct directory. So now we're going to bring all of these client source layer, phaser, configure phaser. So here we're going to define the animations. So we have the player animations that has 2 frames. It's going to cycle, and here you can also you have the coin animation. So here you can set the amount of animation that you have, and also the speed of the animation. So yeah, everything animation related. And now we have to also add some constant variables here into the constant directory. Basically, we added the enum just to mimic how the contract does everything, the same that we define on the mod config file. And here we set up the animation for the player and for the coin. And finally, we set up the system calls in the client mod and create system calls that basically it's going to bind together the TypeScript function, create a TypeScript function that is able to call a basically Solidity function, an on-chain function that sends the transaction. And yeah, we have to also import that, so we put that into the register, into the layer phaser systems. So to be able to call it from phaser, we're going to the register system file and basically add the system that we just created. So yeah, now we're ready to run the game. Let's just go to the root directory and run it. And this will open this interface, like this terminal CLI interface. And in some point you will be able to see the game here, but right now it's loading. So you need to wait for it to just finish loading. So here you have like this client part that is all related to the front end and the phaser front end that we're using, the contracts that basically the deployment of the contracts that it just finished deploying, so the game should be ready now. And oops, my game, oh, I think I messed up a name. So this is lowercase. Oh, this is good to something good to mention is that this should have like fast reload, so you don't need to redeploy anything. So it has just, as you can see, say waiting for file changes. So as I just did now, I just made a change and it updated like automatically. And yeah, the same for the contracts. If you make a change in Solidity, it will be automatically a change on the front end. So as you can see, the coins that we put on the like constructor or post-deployed script are now on the screen now. They were deployed, and as you can see, these are the 3 coins in the coin position. And I want to show you the player coins. So right now the player has no coins, but I can spawn it here and he can move around and start collecting coins. As you can see, he collected 1, he collected 2, and of course, if we open another one, just basically client, you get like multiplayer by default because this is blockchain, open protocol, and he can also play around. So yeah, this is the first demo. I hope that everything makes sense for you. So if you have any question, no matter if it's too new, remember this is a combination of a lot of things: Solidity, front end, like gaming, and yeah. So remember, yeah, just ask any questions if you have. There are no too basic questions. If something that is too advanced, I can go and ask for more advanced people. And yeah, just feel free to ask. Now we're going to move into the private part. So how do we combine this public aspect of Solidity? Because in Solidity everything is public by default. How do we combine that with a privacy state? So we'll do that in the next one, in the next part. See you then. In this next part, we're going to start building a autonomous world using mod, but also with a private state. So basically using Circom to do private computation. So what we're going to do is a game where bombs are hidden by a game master or the environment, the game creator hidden some bombs, and the player can move around, and if he walks into a bomb, he will die, he will explode, the bombs will explode. And the thing is that he doesn't know where the bombs are located. So yeah, we're going to combine a prover with that is able to prove with off-chain computation. By that a player step into the bomb, we are revealing the actual position of the other bombs. So yeah, let's start building this the same as we did before. We create a new mod project using Phaser. Next, we are going to define the public state. So here we are going to define the mod config file here. So the same as before, we remove the default and we put here. As you can see, the changes are that we are not using coins anymore, but the player is the same. The thing is that we added this isDead boolean that is going to set to true when a bomb is exploded, and also we added some zk state. This is going to be like this commitment will make sure that the game creator, the one that set up the bombs, is not able to cheat later on. We're going to see more about this in a moment. So then we're going to go to create this Circom file. Yeah, before that, let's create the whole directory structure. So we're going to create this directory structure that is very similar to what, just to following up to what the structure for the projects on mod. So in this case, we have a zk folder where we're going to place a detonate bomb.zk .circom file. So this is all the off-chain computation, all the private computation. So this function receives, or the circuits receive as parameters the bombs, the bomb 1, 2, and 3, and the player position. For each of them, X and Y. And the return, that basically is going to be public to the contract, so to the whole world, is going to be a commitment and a result. The commitment, just to make sure that no one is cheating, and the result is going to be 1 if the player is actually stepped into a bomb, and 0 if he's safe, basically. So the first thing is just hashing all the bombs position, the bomb 1, 2, and 3 position. So basically we hash together these 6 elements because each bomb has X and Y. So we hash it out and it will give, this is basically the commitment. So this is going to be stored on chain, and this is, basically contains all the information of the bombs. So this is just for so the environment is not able to cheat. Now we're going to basically compare if the player position matches with the bomb 1 or A, the bomb B, or bomb C. And if at least it matches with 1, it's going to just return 1 as result. And that's basically that's our secret. We're also going to check it, so we added some log here just to check it before we are implemented on chain. So in a summary, we pass as parameter the bomb 1, 2, 3 and player position, and the public inputs to the contracts are going to be the player position itself and the commitment and the result. So let's try it out. We're going to also need the Circom lib library, because we're using Poseidon and we're also using the Poseidon hashing and also the comparators libraries. And before we deploy this, let's just give it a try. Let's add an input.json just to check if everything is working correctly. And we are going to generate a proof like this. And as you can see, these are the parameters that are going to be passed privately to the circuit. Well, the bomb is going to be private, the player is in the end is going to be public, but the inputs to the circuit are the 3 bombs position, the position 1, 1, 2, 2, and 2, 3, and the player that, as you can see, stepped into the last bomb because it's on the position 2, 3. So once we run the test, you can see that 1 is returned because the player actually stepped into a bomb, and this is the commitment. We need this commitment that is done in a way that basically hashes all the position of the bombs, but is put on chain, so he doesn't cheat. Remember that if the word is too small and there are too few bombs, this is going to be, the players can attack by brute force and basically reveal the whole bomb position. But if the word is big enough, it's going to be practically impossible to, it would require too much computation to hash it. So let's now just, before deploying this, let's just try it out. What if the player is in the position 3, 3? There is no bomb here. As you can see, the result is 0 because he's not stepping into a bomb, but the commitment stays the same. Okay, so now we're going to just create the ceremony. Remember that we're using GRUT16, so we need to generate the circuit for this and the contract verifier contract, and that checks on chain if all the computation is done correctly, checks for a proof. And we're just adding some entropy here. This is something specific to GRUT16. And then we are going to also copy some files here to the prover directory here. So we copied these 2 files here, and also we generated the prover. I want to talk about the prover at the end of this section, but the contracts in the contract directory, we added we also generated this contract here. We added here, and this is going to be able to generate proofs that are going to be generated by the environment. Okay, so now let's go into start onto the contracts. Let's just go to the root directory, remove some default files that we're not going to use. Now we go to the system directory, and I'm going to create my game system.sol file, and also we're going to add a post deploy script here for it to be initialized. So what does my game system does? So it moves the same way as it did before, remember? But now the only difference is that he's not collecting coins. Oh, by the way, there's something very important change that we need to do here. By the time that you see this, it's going to be fixed. There is something for the indexer to be easier to implement. So yeah, this change. This will make more sense later on this video. But yeah, so here the movement is the same, but we're not collecting coins anymore. The spawn is also the same. We'll just be able to click on the map and spawn the player, but the detonate bomb, it is going to be different. So here, we pass a zk proof. We pass a zk proof to basically prove that the player is in a certain position, and if the result of the proof is 1, it means that the player is stepping into a bomb. What else did we check? Basically, if the players are already dead, we won't just re-execute the function. Also, the player has to be in the same position as the proof that we pass is. And also, yeah, we just check if the commitment is the same as we stored it on chain. And yeah, if all that is true, or if that is correct, then we kill the player by setting it instead to true. And yeah, so basically now, remember that this is how you set up variables on mod. This is how you interact with the mod system itself. Okay, so now we are going to, into the post deploy script, we create the grot16 verifier. We deploy it, and we deploy it here, and we store it on chain like this. The verifier address gets deployed from the constructor or post deploy script, and also we store the commitment. So this is going to be stored on chain just to check it exactly here if the commitment is the same as the one that is stored on chain, but we need to calculate it. So in order to calculate it, you can see that this should be super up here. Okay, so the commitment is, that's why I was printing it, because depending on where you place the bombs, it's going to be the hash of the bomb, so that's going to be your commitment. So if you put the bombs in a different place, you will need to update here, like just store it in a different place. Just basically make sure that the commitment is the same as the place that you the bombs are placed, and you have to store it on chain so it can be checked in the verify function from detonate bombs. Okay, so now let's go into the client, and let's go to client, source, layers, phaser, systems, and I'm going to create my game system.ts. Okay, oops. So here, what we do is pretty much the same as we did before. This handles the player movement. That's pretty much it, and also the animations, the dead animation, and also and also I added some. If you press I, it's just going to put just basically printing the screen where the bumps are, but this is just like graphical stuff. The player shouldn't be able to know where the bumps are. And now we're going to add some sprites. You can use mine, just right click save, but I have them here. So I have the dead animation, the player animation, moving animation, and also the bump. So I'm going to place them into the arts directory. Okay, so now we build a tile set. Yeah, like this. And now we should be able to configure phaser. Okay, so let's go to layer phaser, configure phaser here. So here we configure the animations as the same as before, but now we add the dead animation and the bump just to print it on screen. So now we add the constants for the animations and also the direction just as before. And now we bind everything together by registering the system here. We add our game system we register it. And also finally on the client mod directory, in the create system calls, we add the two interactions that we're going to do on chain, which is spawn when we click and move when you click WASD. So now we are ready to, we should be ready to just launch the client, and we will be able right now to just move around, but the bombs won't detonate. So in order to do that, we need to run the prover backend. So we open a new terminal. Oops. Okay. So here we open a new terminal and we install snark.js and enter.js. Also Express, going to be an Express server. So we add this file, which is going to be the backend. The prover, the environment prover. So let's see, zk-prover, and we add server.js. So this is going to be listening to each player movement, and when he detects that the bomb is in a certain position, that a certain bomb is in a current player position, it will submit a transaction on chain and will detonate the bomb with the proof, with a zk proof. So here bombs, prover bombs.json, prover, we are going to add a we're going to add a bombs.json, and just with the bombs location that is going to be on the backend. And now we're going to need to set up some variables. So here on the server.js file, you need to set up the contract address word. The private key, you can use this one because this is the default one from that mod uses from Anvil. But yeah, of course, if you launch this on production, just set up with an account that has funds, some ETH, that is able to send transactions on chain. And you're also going to need the player table ID. So the contract address word, this you can grab it from here, is this one, the word access. Just copy this, and this copy mode doesn't work on my Linux machine, but yeah, just try a different terminal. From me, the one that worked is this one, the one from Visual Studio Code. So yeah, just copy this contract here, and the player table ID, you can get it from the front end. So basically you can go here, components, it's the registered tables, I think. Yeah. Player, you can look for player. So I'm an editor here. I realized the audio is missing to this part, so I can just finish it by narrating it. So as you can see, once you place your player table ID for your player, you're now ready to run the node server. So now once it started, it's going to start listening to player movements. So as you can see, the bombs are there. I'm going to spawn a player. The backend prover is going to detect it, as well as any movement that you do is going to detect it, as you see. And he knows the position of the bombs. So when a player gets into the bomb, he will be able to send the proof on chain and explode it. Of course, a lot of caveats here. He still needs to do it fast, so he can prove it on time. But yeah, I hope this this part help you, and see you on the next part where we're going to do on-chain proving from the browser, not from an external proving. Now for the third and last tutorial that we have in this video is about making a PvP combat system where you attack your opponents and defend, and all the proving is not done in a prover backend but on your browser. And in order to test that, we're going to do it with this demo that I built, that you have is inspired in both this Stratego, the board game, and all the autonomous board that has been happening so far. And basically you can move, you have some units that you can move around in a public state, and in the private state you can combat another unit. And as you can see, some question marks are shown where the opponent's positions are, like units position are, but units or characters are, but you don't know which types they are, but you don't know the stats they have. So yeah, basically you will be able to attack by making a zk snark that you are proving that the unit that you have is the one that you committed to the beginning in the game, and you will be able to defend by producing another snark that is able to like give away the result, calculate and prove the result of the battle without revealing your type. So in order to do that, as we mentioned before, we have this type of unit. We have the dragon, this is more powerful, that is able to defeat the mage, is able to defeat the ogre, which is able to defeat the knight, and the knight is the weakest one, but he is the only one that is able to defeat the dragon. And we're going to, just like before, we're going to use mod to do the public state. In this case, it's going to be the movement, the positions of every character, and also the commitments, the zk commitments. And the private state is going to handle the battle attacks and defenses. So yeah, let's get started. Maybe this will make, yeah, I hope this will make more sense once you're trying it. And yeah, let's start with the state. The state, as you can see, we have the same moving as before, move enum. We have the characters positions that are public, that are on chain, and they have some stats added to it. Now, one player can have many characters, so basically we would just move them around, drag them around every unit. So each character has an owner, and they also have an ID to be able to differentiate between them. And they can be attacked. So we'll store who attacked, what's the level or the type that the attacker has, and at what time it was attacked. This is important. This will be more important in a moment. This will make more sense in a moment. Also, when you attack, you reveal yourself. So if you are already revealed, this is going to be publicly visible, and also a boolean to detect if you are dead or not. Now on the private state, we have some commitments, but now the difference is that we don't have like a word commitment, but we have each player has its own commitment to their characters. So basically when you spawn, you commit to the your character positions, and yeah, without revealing them by using a commitment. Okay, so yeah, we're also going to have two verified contracts, one for the attack or reveal and one for the defense. Okay, let's start with the attack circuit, which is also, I also call it the reveal circuit. Oh, before that, let's just, I didn't add the state. Let's start with the state, sorry. Okay, so in the contracts and mod config, we replace it with our new state, with our new table schema. Now we create the reveal circuit. And then the defense snark. Okay, so what they do is, okay, so the attack snark or the reveal is snark is or Circom or circuit is receive. So basically, you have all these characters. You hash the type of the character. For example, 1 is for dragon, 2 is for mage, 3 is for ogre, etc. So you hash the types in a way that each type is different, and there's one of each type at least. So you can have like 4 dragons, that wouldn't make sense. So the zk proof is able to check a commitment in a way that the commitment itself is valid. And to check that, we do it like off-chain, you know, like you just make a commitment on-chain that is the result from this. So also we add some private salt, because otherwise it will be very, very easy to make a brute force attack. And yeah, then we set the which character are we revealing and the value, the type of character that it is. And yeah, this is basically say, okay, I'm attacking with the character 2, which is a dragon, which has a value 4, for example. And then we hash everything together. We hash all the characters' position with a private salt. The private salt is able to make us like invulnerable to brute force attacks. It's like you can think about it like a private key stored in your browser. Then you basically compare if the character positions, everything is valid. And at the this can be done like super straightforward in Circom, but you have to check that at least it exists, like at least there is one of type 1, one of type 2, one of type 3, and one of type 4. So there is at least one dragon, there is at least one ogre, there is at least one knight, and one mage. And yeah, so after that, we're going to check that we do that for each of one of them. And also we check that the character that we are revealing is in case the one that we say that we are revealing. So yeah, 2 checks. One, to check if the reveal is valid, and also one other check to check if the commitment itself is valid. The defense snark is a bit different, but yeah, it's the same idea, but basically you receive as parameter the target that is being attacked and the level that is being attacked. So basically in the defense snark, you are going to prove that the attack that you are receiving is not basically if a knight attacked and you are a mage, you're going to reveal that, okay, you want the defense, but you won't reveal why you want it. But because, for example, the knight, if the knight attacks the mage, and the defense is going to be is going to be it's going to pass the defense, but the attacker won't be able to know if the defender was a mage or an ogre. So yeah, that's what we do in the defense snark. Okay, so let's just compile them. We're also going to need the Circom lib library because we're using Poseidon hash and the compilers library. And yeah, let's just go into the directory, reveal, and do the ceremony. Okay, so remember that we're doing growth 16. So we need to go through all of these, and also remember that the output this time is going to be 2 verifier contracts, one for the reveal circuit, and the second one is going to be for the attack circuit. Okay, so this is the attack or reveal circuit. Now we go to the defense. Okay, we compile, and we also do the ceremony, and also we are going to need to put the artifacts. Actually, we don't need this create directory, only this. Okay, here you go. Now we copy the directories, and now we're going to go through the, oh, by the way, you also need to go to change some names from some contracts. So here, the defend verifier, you have to put the name defend. This is so when we deploy them, because we're going to deploy them automatically. So when that happens, yeah, you will be able to distinguish between the two contracts. So yeah, just put reveal and defend in their names. Okay, so now we go back and delete the unneeded files as usual. And now let's build the my game system.so, the game logic. So as you can see, the logic is pretty much similar, just move around as we did before. But the different thing is that here, when you attack, you have the attack and defend functions. So it will basically check for the proof that will receive as parameter, and basically it will return a result, and it's the defense one. Then it's going to clean the stats of the attacker, because when a player gets attacked, you won't be able to. I was checking the sound because the last video I had some issues with the sound. So basically, when you receive an attack, the player will get won't be able to move, and when you prove your attack result is going to be like clean from this state. It will become back to the normal state, and of course, unless he dies. So we check that to heal, and there is this function that we're not going to be using in this example, but it's just to kill an unresponsive character. Of course, if the way the game works is that you attack someone and he has to defend, but if he dies, he has no incentive for posting that on chain. So if he doesn't post that, we can just call this function that after, I don't know, 1 minute, if he didn't respond, you can just kill it without a proof. Yeah. And lastly, here in our like post deploy script, like similar to the constructor, we're going to deploy the 2 verifier contracts, one for the reveal and one for the defense. Okay, now we are going to go to the client, and in the client we're going to set up the movement and the drags, because here the way it's going to work is not just with the keyboard, but with dragging with the mouse. So when you move to an adjacent square, you'll do that by dragging your character, and by connecting to character with the mouse, you're going to be able to attack, and by just clicking it, you will be able to defend. So this is done like here in the phaser client part. Now on to the client-side proving part. First, we need to install Snark.js, and then we can create the system calls. Create. So this is on src mod. Create system calls. We're going to have the spawn. When you click, you'll spawn your characters. No CK needed here. Move also, just move around by dragging, but also no CK needed here. The attack and defend, that they do need some CK proof. So here you can see how we generate a proof, this time on the client, by importing grot16 from Snark.js. And player entity, this is not like an on-chain transaction, but this is just reads the position from the player. This will also be needed in the front end. Okay, so now for the animations here, if you want, you can use the same as me, just as before. Just right click and save them. We're going to put this in the art directory, in the sprites directory. Skip this. Okay, so now we're going to generate a tile set. Just going to the art directory and run this. Okay, now we're going to configure phaser to add the animations. Okay, configure phaser, we add the animations, the dead animation, the attack animation, and the constant. Define the constants here, and we register the system. Okay, now we should be able to run the game. Okay, here you go. So we need to wait for the transaction to go on chain. Of course, this will make a lot of sense to have it on two separate windows. So I'm going to use two separate accounts here. Okay, here you go. Okay, so I think this is ready now. Let's just refresh here and put the client here. So wherever you click here, for example, it will spawn the characters. But as you can see, they are visible to this player because he's the owner, but this is not visible for him because yeah, he's the opponent. So he can also spawn, and the same thing will happen. And okay, so what happens if the mage, or better yet, the knight attack the mage? I think this is a good example. So he will put it in an attack defense. Oh, by the way, you can move. So you can see you can move. And yeah, but you can move, of course, you can move your opponent characters. And when you move, the opponent will see where the unit is, the character is, but he don't know what type it is. Okay, so the knight attacked the mage, and as you can see, he revealed himself. Who is he? And the defense doesn't have to reveal himself. So to do the defense, you can just click the unit, and it will go back to normal, and it will be kept private. But what happens if he just attacks the dragon? he won't be able to defend and he's going to die. So yeah, so here this is not like a complete game that is ready for production, but what I want you to like see or understand about this is that you can have like this private state combined with public state on blockchain and specifically on autonomous world. So let me know, what do you think about autonomous worlds? What do you think about ZK combined with it? I'm also going to release more content about ZK. I mostly have that on Spanish. I also leave it in the description if you know Spanish. But yeah, also going to just be doing more content about autonomous world because I think this is so much potential. It has so much potential, and yeah, we need more documentation, information about it. And yeah, thanks for watching, and see you in another video. Bye.